Hello, it's my pleasure to give you this presentation titled Biophysical Limits to Growth as part of the Alternative Economic and Monetary Systems summer program which you're participating in. My name is Brian Fath, and I am a professor in the biology department at Towson University in the United States and also a research scholar at the International Institute for Applied Systems Analysis in Austria, which would be just down the road from where you would be taking the course in Vienna, and we'd probably have even had a chance to meet, but I'm actually in the US now as well, unable to travel. So my background is in systems ecology, and that's a field that uses holistic systems thinking approaches in order to understand energy flow and biogeochemical cycling in ecosystems, and then also to apply these ideas and knowledge to social economic systems. And so this presentation is going to be looking at what nature can tell us and what biophysical aspects can tell us about the limits to growth. So one of the things that we can start with as an observation is that there are a lot of unsustainable human ecosystem interactions that are all around us. And why are people making these mistakes? I mean, you could say they just had the lack of knowledge about how systems work, but maybe that's an excuse for the past, but why do we continue to make such mistakes today? You could even ask yourself the question that is it inevitable that we must degrade the environment to satisfy human needs? Is it a zero-sum game where there must be losers if there's going to be winners? And part of what I hope to get across in this message is that we're looking for win-win situations where both environment and humans can succeed. Well, one of the reasons why I think we have these unsustainable interactions is because the core driver of all of that is the presence, the growing presence, increasing human population on the planet, because people need places to live, they need agricultural outputs to sustain themselves, they need to move around, and energies and resources to do that, and so on. And to do all of those basic human requirements takes energy, material, resources. Those, of course, are coming from nature, so they are extracted through the application of land use change and deforestation, altering the biogeochemical cycles in order to get the resources. And of course, those actions then lead to the symptoms that we see, such as climate change, eutrophication, acid precipitation, and so on. So it's from the first causes, the first principles that lead to the environmental degradation and symptoms that we see. So how do we make the decisions that we do in order to satisfy those needs? And clearly economics is a big part of that. It's one of the main organizing forces in society and how resources are moved and how decisions are made. And many of these decisions then are going to be made based on cost-benefit analyses. But we also know that the true costs, the direct plus indirect costs to individual society and the environment are also often not known. So this idea of externalities and factors that are not part of that decision making skew and obscure the best decisions that we perhaps might be able to make. And if you look at the economics approaches towards understanding things like growth, and the classic economic growth models is the Cobb-Douglas production function. And the idea is the output, or the growth on the left-hand side, is essentially can be described by three main factors. One is the total factor productivity, C, but then also a function of the labor and capital. And the first thing that really should jump out at you at this equation is that there's no environment explicitly part of this, that growth can happen independently of the environment. We see this also then, is growth a means or an end? I think something even as basic as that. If the goal is just to grow, then you're obscuring again the fact that growth is a means to something. You're growing for a purpose. You're growing for something. So asking, what is actually the purpose of the growth? You can see GDP is going up over time in the 20th century mostly, but alternative indicators often tell a different story. So growth of one indicator might not correspond with growth of other indicators. And does bigger always mean better? Another question that we don't often ask ourselves, really. We always think that if you have more, you're better off. But as the cartoon on the right is showing you, that there are a lot of social and psychological studies that show that people still aren't satisfied just through having lots of things. And furthermore, humans are social animals. We measure ourselves in terms of others. We have relative needs, not really absolute needs. Once you get past a certain basic minimum set of requirements, and so we're always looking to have in comparison to others. And so the whole scale can either be raised or lowered depending on the cultural context that is in. So there was an article in the New York Times that came out a couple of years ago where the author was talking about the observation that growth had been lower in the last few years at that time than they had seen really in the last couple of generations. He's saying longer in the lifetime of most people on Earth, referring to this as a low growth world. And he goes on to say that it's looking as if there's something fundamental broken in the global growth machine, and our usual ways of fixing it aren't working anymore, although that we should still keep trying to do that. And I think it's really interesting to note that he's referring to this global growth machine as though there's this expectant machinations of process that are going on that are driving the system to churn this growth out, right? And taking that as an unquestioning fact, but then also going on to say, oh, but we really can't control it the way that we used to just by tweaking interest rates or fiscal stimulus through Keynesian approaches. But he does, of course, say we should continue to try to do that. But to me, the most interesting thing about this very long and detailed article was that there was never any mention of natural resources or the environment as potentially one of the constraining factors to the growth that he's so much expecting and looking forward to. And this gets back to really just the basic assumption error that underlies most economic models, where you have the economy as an isolated system. Your classic circular flow diagram shows households and firms that are exchanging money in terms of incomes and spending, but then also exchanging physical resources in terms of goods purchased and then labor being given to the firms. Well, the problem with this picture is that it's a perpetual motion machine, that it shows this circular flow being able to continue indefinitely without any connection to its natural environment. So a much better model would be to represent the economy as an open system where you still got household and firms that are circulating goods and services and money, but there's energy that is coming in, matter and energy that is driving the system, and then there's waste generated at each stage as well too. If you back up even a slightly larger scale, you can think of that as the biosphere, right? So we've got the Earth here, and you've got the solar energy that is coming in and driving all the processes on Earth, and you've got low-grade thermal energy that is being dissipated back to space. And within that bounded system, you now have everything else going on in terms of not just ecosystems, but the socioeconomic systems and the economy. So it's giving you a different perspective that the economy really only functions in the presence of these other flows. Therefore, understanding something about those flows is critical. So let's look back a little bit about the history of recognizing limits. Thomas Malthus was credited as being one of the first ones to really look at the connection between human population growth and food production. And basically his assumptions were that population can grow exponentially, whereas food production will grow linearly due to the increased land under cultivation. So therefore he was predicting there will be some time when the population exceeds the food supply. This is nowadays even seen as kind of a Malthusian doomsday approach, that we're going to cross that carrying capacity threshold. Even with almost 8 billion people on the world today, we have not crossed that. Food production has managed to rise. That doesn't mean that there is not ever going to be that threshold. But he was writing this back at the late 1700s when he was first putting forward these ideas of recognizing the physical constraints. More recently, but still late 19th century now, George Perkins Marsh, very important American environmental scientist, wrote a book called Man and Nature. And he had a very interesting line in there where he said a certain measure of transformation of terrestrial surface, of suppression of natural and stimulation of artificially modified productivity becomes necessary. This measure man has unfortunately exceeded. So he's saying, of course, humans need to modify their environment in order to get the food and the resources they need, but that he's saying back then, unequivocally, we have exceeded this threshold based on the evidence, largely soil erosion and other agricultural-based factors. Um, you can read that on your own. Another person more recently, and we're moving up into the 1940s, Aldo Leopold, a very important writer. He was considered one of the most influential writers on conservation. So Sand County Almanac is something I would recommend. In there, he introduced this idea of a land ethic, which is what he defined as a thing is right when it tends to preserve the integrity, stability, and beauty of the biotic community, and is wrong when it tends otherwise. So what he's introducing here are not just physical limits, but actually moral limits. He's giving you an ethical basis to bound your decision making. Don't do something if you can, if it's going to hurt nature, if it's going to hurt the biotic community. So he's now enlarging the boundary of the community to include soils, water, plants, animals, or even collectively the land, as in the land ethic. But it's not just about human needs, but it's also about the biotic community. Then we can jump forward to the 1970s. Donella Meadows, the lead author in the Limits to Growth study, which was supported by the Club of Rome. And in this study, it was one of the first systems dynamics models to be applied at the global scale to look at the interaction of things like agriculture production, human population growth, industrial production, pollution, and so on, and to basically come to the conclusions based on the model runs that you can't grow indefinitely. And it seems pretty clear to us, I think, from a systems dynamics point of view. But their results were able to show that the only long-term sustainable solutions were one that reached some sort of stable, steady-state conditions in terms of population and resource consumption. That when you've got one planet, you can't continue to consume resources at an ever faster rate. Coincidentally, 1972 was also an important year because this photo was taken and released, the blue marble photo from one of the Apollo astronaut missions, and that galvanized again these ideas of having one Earth, one spaceship, one planet flying through space, where all the resources are, all the water, all the soil, all the nutrients, all the people are essentially on this one spaceship that is bounded by the edges of the planet. You see space or you see the planet, and so these ideas of limits to growth and boundedness were really taking shape and helping to provide the foundation for the early days of the modern environmental movement. One of the things that they advertise nowadays, this idea is that there is a overshoot day, the day when after which we have used all of our resources granted to us for that year. So for example, in 2018, that date was August 1st, meaning that the amount of resources that are renewably available to humans were consumed during those first 7 months. But then everything from August 1st on was essentially over the carrying capacity in the range of overshoot, taking resources then from future generations to be able to utilize theirs. And this date is actually moving forward. Now it'll be interesting to see this year with the shutdowns that we've all been experiencing, whether or not the date actually moves back a few days, which I would expect, but this hasn't been announced yet for 2020. Continuing on in our story about the limits, Jane Jacobs wrote a book in 2000 called The Nature of Economies, where she was looking at the limits to growth from the point of view of how to work with them, right? So she's saying natural principles of chemistry, mechanics, and biology are not merely limits, they're invitations to work along with them. So we see now this spin towards limits as not being a negative or pejorative thing, but limits as being something that having that knowledge allows you to work better, to work with them, to make a difference that way. And this positive spin, I think, makes a difference because I didn't mention this before, but with the Limits to Growth book that came out in 1972, part of the reaction to that was negative was because it was seen as pessimistic. Again, it was seen as something where we don't want to be told we can't do something. We don't want to be told that there's limits. And so recognizing that that limits aren't always a bad thing has been, I think, a step forward in this discussion. This also continues into a movie and book that came out a couple years ago Sunita Narayan was quoted in there as saying, there are limits, but let's celebrate the limits because we can reinvent a different future. So again, this idea of celebrating limits, I mean, it's such a different concept as what we usually think about in terms of limits as being constraints and barriers and something that we want to push through. She's saying, no, they're limits, that's okay. Celebrate the limits, step up to the limits, but then think, okay, what can we do differently now? How can we reinvent a different future? So we're flipping our mindset on how to approach and deal with limits rather than burying our head in the sand and saying, no, there are no limits. And then one last example is that this book also came out in 2015. I was co-author on, called Flourishing Within Limits to Growth. And the idea here is that ecosystems do quite well under constraints and the limits that they have. That one planet, the picture that I showed you earlier, is showing you the whole set of resources that we have on this biosphere. But what can we learn from nature, right? How can we redesign things and do better based on how nature has been doing things already for billions of years? And in that book, what we did is we outlined 9 basic properties of ecosystems. And without getting into too much of the technical detail, just to give you a little bit of the flavor for it, the first 3 had to do with material constraints. And these are the hard laws that every discipline, whether you're economics or engineering or physics or ecology, have to deal with, or sociology or law and so on. The first and second laws of thermodynamics. I mean, energy is the key motive force for everything, and energy is going to be conserved, and energy is always going to be dissipated as you are processing it from one form to another. And then you've got the chemistry side of things. You've got a periodic table that has certain biochemical constituents that link up in certain ways and not in other ways. So those 3 material constraints are the table upon which we're playing, you could say. Now, on top of that, we have these ontological properties, these emergent properties that come from those interactions. And the first one, the way we describe it, is that an ecosystem uses surplus energy to move further away from thermodynamic equilibrium. Basically that's saying that nature grows. Nature does move further from thermodynamic equilibrium. It's a physically driven biological aspect. So one thing that biology does is it takes energy and it uses that energy and converts it into more material and makes more biomass, right? So really the key feature of biology is that it's able to replicate itself, it's able to grow. The second aspect, though, is that ecosystems co-evolve and adapt to prevailing conditions. So there's a dynamic context in which these ecosystems are part of, not only because of natural considerations, but because the other biology that is also taking place in that space. So we have a biologically driven biological aspect. So those are the 2 things that actually are not going to be in a physics book, because these are biological aspects. The physically driven biological aspect, which is the growth phenomena, and then the biologically driven biological aspect, which is the evolutionary and adaptive phenomena. Okay, then these last 4 properties have to do with things that we observe, the phenomenological properties, and basically these are saying that what we observe is a lot of diversity. The niches get filled through different structure and functions. Ecosystems also display a great deal of networking that allows the resource flow to be utilized efficiently and effectively. There's also a fair number of hierarchies that emerge in ecosystems, and there's an enormous amount of information, both in terms of the diversity information, genetic, biochemical, and process information. So again, we have a book on this that you can read for more information, but these 9 basic principles we think are a good description of ecosystems, and then to be able to understand these and to try to apply, they don't mind apply perfectly in all situations, but to the socioeconomic systems in which we are trying to manage and govern as well. And again, one of the ideas here is that ecosystems have that growth stage. So there's this idea of succession, where ecosystems grow from early stages to later stages, and during that they can follow something fairly straightforward like a logistic curve, where the biomass or the complexity or the amount of energy through flow are all going to be increasing, but they reach some sort of stable climax state at the later stages where the growth is giving way to stasis. And a good way of looking at this, and this is presented actually in E.P. Odom's 1969 paper, is a bioenergetic model of succession. And what we have here, the terms are the production, the gross production, the overall amount of photosynthetic activity that's taking place, the net production, which is the net that's available to do new work. The R is the respiration, which is essentially the maintenance costs of the organism, so it has to do metabolic activities and respire. And then B is the biomass, so the total amount of biomass. So down here again at the early stage of succession, you've got very little biomass. The idea is, forest fires come through or some sort of disturbance and the land is cleared, maybe an agricultural field that had been left abandoned. So very little biomass, therefore there's very little photosynthetic activity, but there's also very little metabolism and respiration going on. As some plants get established, those plants leaf out, there's more green material, so the gross production is the fastest thing and the first thing to rise. But of course that plant is also going to have some respiratory costs and so on, but the biomass is increasing. So in those early stages of succession, the production is much greater than the respiration, and the additional excess energy can be channeled into growing that system. So these early stages, the net production is positive and even growing positive, and that allows the system or the organism or the ecosystem to grow quite rapidly. However, in the later stages of succession, what we notice is that the production costs are level off at some point just due to the biophysical reality of the space. Maybe water is limiting, maybe light is limiting, maybe temperature is limiting, or nutrients and so on. But the respiratory costs will continue to rise basically up until the point at which the system is now in some sort of stasis. So when the production, when everything that is being produced is being spent to maintain the system, there's no additional benefits for the biomass to continue growing. So that's the causation for why stasis occurs, why things don't grow forever, because the growth costs you something, and maintaining the growth costs you something. And at some point, you're going to run out of the net production that you can invest in additional growth. Okay, so it's useful to think then of growth as the quantitative increase, that the actually getting bigger of something, whereas development then would be the qualitative increase, the changing, the improvement, the efficiencies, the adaptations that take place there. And I think there's this nice quote that says, we must realize that growth and development are two very different things. You can develop without growing and vice versa. And so separating, is the system growing now? Is it developing? Does it need to grow? Does it need to develop? Will help you understand a little bit more about limits to growth. And we put this forward in terms of these ecosystems again, and without going into the detail here, I just want to point out that there are different ways of tracking how ecosystems get bigger, how the biomass increases, how the energy flows increase. But there's also ways of measuring how an ecosystem gets better. What is the network like? What does the food web interaction pattern look like? Is it more articulated? Is it more redundant? How much information is in the network, right? So we can now distinguish between bigger versus better, and one is growth and one is development. And that also, I think, goes a long way in this discussion. Okay, so let's say something about the importance of scale, and thinking back to that nice snapshot of the planet Earth, and recognizing now that we are approaching 8 billion people on this planet, rising quite rapidly from reaching the first billion only in the year 1800, even though the species is 250,000 years old approximately. So all that time period to get to the first billion, and only a few centuries to get the next 7 billion added there. The projections are going forward quite a big range. Some projections have actually increasing to a peak and then coming back down, whereas other ones have it continuing to rise almost on the similar trajectory. A lot of assumptions go into those, and my goal now is not to discuss those. We can actually come back to the live discussion if you want to. But the point now is really just to show you what that does from the planetary perspective, is the idea that back when there was even a few centuries ago, even only a few centuries ago, the idea that the human population was relatively low compared to the resource base, and that was referred to as the empty world by some of the authors, because you still have that economy with the material and energy flowing in and out of it, but the economy was a small subset of the overall ecosystem from which was embedded. And over those centuries, now we've gone to what is referred to as the full world, where the scale of the economy has expanded so much, the scale of the human presence has expanded so much that we are now again pushing up against those margins, that there is some carrying capacity, there is some physical constraint on just things as basic as the space and resources on the planet. And it's happened so quickly. Over here in the text, I'm pointing out the fact that the customs that we have, the laws that we have, the religious organizations that we have were developed under an empty world. And therefore they really aren't appropriate in giving us the right messaging on how to function under a situation where we are now pushing up against those limits. So we need to think about evolving, right? The evolution and adaptation of customs and human traditions as well to meet the times that we are currently in. So let me say something briefly about the current situation that we've been in for the last few months now. There was a paper that was published. It was a letter to the editor. It was not a scientific article per se, but it was published in our journal Ecological Modeling, where the author was looking at the idea of coronavirus outbreak as a symptom of Gaia's sickness. Of Gaia, I didn't talk about. You might have heard this as a way of describing the self-organizing cybernetic properties that are going on the planet at the planetary scale. And the author was trying to be provocative, right? To say that the coronavirus is some ways that Gaia is getting back at us, right? The planet is getting back, or at least the planet is exhibiting the sickness that is coming out in this current virus that we have. Some of the evidence that was actually in that particular paper, more of the observations of how things have shut down. So here's in China. This is the amount of nitrogen pollution, and you see in January, even just earlier this year, how the concentrations of pollution were quite high around Beijing area, and by February, when everything was shut down, how much the air had cleaned up because the activities that the humans were doing that we usually normally do, normal under the new normal, the old new normal. Same thing in Italy. So here's in Italy in January 2020, northern Italy in particular, and by March 2020, it had taken a breather, so to speak, right? And so on. So there's many different examples. I recommend you click on this. I know mine won't work if I try to jump out of my recording, but this is a Flight Trader website, shows you the number of flights that have been reduced over different parts of the planet over these last few months. And what's amazing is to see how many flights we used to have actually, but some of the impact there. You can also see so these are some NASA satellite photos of California and what Los Angeles was looking like in the Central Valley. So pre-shutdown versus the full shutdown. Los Angeles still has some air pollution there, but getting better by the time you get a little bit later in the shutdown. And of course the Central Valley. So the air has been cleaner. So this reduction of the pressures of the human presence has had a very quick and observable impact on nature. And then the last one I'll show you along these lines, which you might have seen already, was Venice. In 2019, what you see are a lot of boats in the canals. You see the waters as being fairly turbid from the boats, and so there's a lot of sediment. That's the darker color. And then in 2020, you see the water has very few boats, but it's also darker. It's stiller. It's clearer, so that's why you saw some of the fish and other organisms coming back in those waters, which otherwise they wouldn't have wanted to swim in because of all the mud and sediment that is continually kicked up by the boats and tourist industry that are there. So, okay, so how does this all relate then to the alternative economic and monetary systems course that you have? Well, I think we're getting a pretty strong message here that that nature does things one way, and human economic systems predominantly do things another way. And it was often said that one of the mistakes of the 2007 financial crisis was the rush to put the system back as it was, flaws and all. And so a lot of effort and funds were spent just basically propping up the house of cards again, hoping then that it could recover and keep things going. And there's a much greater emphasis now, I think, with using COVID to build back better, right? So now we've got this pause, we have this imposed timeout. How can we not just put things back the way that they were, but actually to do things in a better way? And what would that actually look like? Well, one of the real pioneer thinkers in this field was a professor economist named Herman Daly. He wrote many books over his career. This one from 1996 is called Beyond Growth: The Economics of Sustainable Development, but I don't think you could pick up anything of his that won't be well written and on point. And what he was saying in this book was essentially, again, that we must be using the first and second laws of thermodynamics as a starting point, because we do not have infinite resources and we do not have infinite sinks for putting our outputs. And so an economist trying to put the biophysical context into the economy. And he would even admit that a lot of his work came from an earlier Romanian economist, Nicholas Georgescu-Roegen, who wrote a very important book in 1971 called The Entropy Law and the Economic Process. Without going into all the details of that, essentially he is again proposing this correct statement that the economy is an open system, that wealth is maintained in the midst of throughput. Nobody gets rich if there's not a throughput of activity on which you are tapping something out of that, right? So it all begins with the depletion of useful matter energy and ends with the return of an equal quantity of spent matter energy back to the environment. So the environment is very closely connected on both ends. It's the source for everything, and it also is the receiver, the sink for everything at the end of that. And so putting these ideas together, we've come up with something called the regenerative economy. This is a paper that came out last year in the journal Global Transitions, and in this one we're putting forward 10 different basic features of what a regenerative economy would look like. The first four, have to do with the inputs and outputs, and then the last 6 have to do with the rules, roles, and relationships. So the first 2 are what I've been already stressing, is the fact that you need to have reliable inputs and healthy outputs. So these yellow arrows, if you get those wrong, then you've already, basically doomed yourself to a failed system. But so renewable energies, renewable resources, and healthy reusable outflows. Well, the number 3 has to do with regenerative return flow. So not only maybe reduce the amount of or not only have healthy outflows, but reduce them by having them feed back into the system itself. So more cycling, more. The idea of circular economy that's in the literature these days refers to regenerative return flow. Circular economy is not the circular flow diagram that I showed you earlier, and interesting how that terminology is. Well, some of these things, as far as the rules and roles, are about there should be high diversity, a large distribution. You need to reach all parts of that network. So you need to have you're going to have the large trunk of the tree, but you also have the fine branching pattern. You're going to see systems that have high degrees of network mutualism. So parts of the network, even indirectly and unexpectedly, helping other parts of the network. It should have a high amount of adaptability and be flexible to perturbations. It should be able to balance both its resilience and its efficiency. If it goes too far down a path of efficiency, then it's going to not be able to respond to disturbance. But if it goes towards too much resilience, then it does not become cost-effective, even just in a resource cost-effective perspective. And lastly, this idea that it should be constructive. The gradients that are being depleted are being used to construct new gradients, not just being exploited and burnt off for one-time use. Well, this is more of a conceptual model that we're putting forward. We're looking for case studies to try to quantify and test some of these ideas, but this is an idea of bringing back principles of nature, principles of an open economy, thermodynamic-based economy into the actual socioeconomic systems that are functioning now. And then I'll just leave you with one more historical figure who played a role in all of this. John Stuart Mill was one of the early classical economists from the 19th century, considered one of the most influential English-speaking philosophers of the 19th century. He was not only an economist, but wrote on a wide range of topics. And in one of his later works, well, actually, I guess it's mid-career for him. Sorry about that. He wrote that perpetual growth and material well-being is not possible or desirable. And I think that's really a strong statement for somebody who's coming from somebody who's actually a founder of the economic theories and the whole economic ideas that based so much of Western approaches for the last few centuries, that he's saying perpetual growth and material well-being is not possible, nor is it desirable. And if you read into the details, that what he was really saying was that unlimited growth is not possible in the environment without destroying the environment in which we live in. And it's not even desirable, because he's saying that why would we want to grow forever? That would just reduce our quality of life. If we're always searching for growth, then we're never enjoying what we have. And he was writing that already 150 years ago. So he was concluding even back then that we should be looking for a stationary state rather than unending economic growth. And there's some really good follow-ups on that today, which we can also talk about in the discussion section about the degrowth movement, which is popular in Europe, or there's a Center for Steady State Economics here in North America, and other movements that are trying to realize John Stuart Mill's dream, so to speak. So, yeah, why have we not learned this lesson? The information is out there. We need to act upon it. And with that, I will thank you for your attention. I will draw your attention to one last reference, which is a book on sustainability that I co-authored last year that touches upon some of these ideas, but also gets into some of the foundational philosophies about holism and reductionism and how we can rethink sustainability from that perspective. And so I would encourage you to look at that, and would be glad to discuss with you material on that as well. So